Oh, sorry. C chart, huh? না না লেজার পয়েন্টার রাখবে না। এখন যদি ফুল স্ক্রিনে যায়, এটা this one. Anyway, I think I have to sleep. I've gone up to this stage. Okay, so essentially having talked about the Geant4 and essentially saying that, okay, I've been up to the three references which I gave. These are the three publications of Geant4 which is used. And right now, okay, I mean, one has to go to on the website, okay, for download, okay, the Geant4, okay, from the website itself, and I think, okay, the latest version is 4.11.1. By the way, I mean, there's a I was talking about a new person, so, okay, from Presidency University, okay, I mean, that's him, and you Shayantan, okay, so you'll be but okay, that's fine, okay, I mean, so I think that's fine with me. Yeah, that was a confusion between you and Arnav, okay, so okay. Anyway, let's continue with Geant4. What it does is provides the tools for particle transport and also to model the experimental environments. Now, prior to Geant4, okay, there have been other tools, okay, which could do simulation of the thing, okay, but what they used to provide is essentially the physics models. I described in the previous lecture what are the things which goes in, okay, when a particle goes through matter. So those things has to be modeled by some source of codes, and there used to be essentially two sets of code which is available and which people try to use that. One is called electron gamma shower code or EGS. Both of them, and the other was the high energy transport code, okay, which came from Lawrence Livermore Library. Lawrence Livermore, okay, I mean, no, Oak Ridge National Library. And the first one was trying to simulate the passage of electrons or photons through matter. So essentially all the electromagnetic processes. And the second one was trying to model the hadronic interaction with matter. Now, the main thing is that both these sources, okay, I mean, of the code were providing interactions of particles in matter. And when it interacts, new particles will be produced. But the thing which it does not do, okay, so for example, if you have a model with a detector per se, the transporting the particles from one part of the detector to another part of the detector, this transportation was not done. And that part was left for the user, okay, whosoever was trying to use to implement himself. So that was a little bit complicated, okay, for anybody to do that. Whereas when the so-called Geant came as I mean, prior to Geant4, okay, it came in other incarnation, because the computing language was different in high energy physics in those days, okay, it was mainly Fortran, okay, I mean, in those days. So when they came, okay, the biggest thing they did, okay, that you describe the detector in full glory. That means you have to essentially describe all the components of the detector, not just the shape and this. I mean, I'm coming to this, the shapes and the sizes of the detector, how you just build it up, but also the material content of the detector. So once you describe that, the transportation part is entirely taken care of by the tool itself. And not only that, okay, I mean, apart from, I mean, obviously, okay, I mean, it can inherit all the physics models, okay, coming from EGS and high energy transport code. But not just that, okay, I mean, it also tries to develop further, okay, the physics models. And if one sees that most of the codes can, I mean, particularly for electrons and photons, the interactions are well described by the theory. But in case of hadrons, okay, I mean, it is not so well described by theory. You have some approximation which can do a fairly good job at high energies, but when it comes to low energies, it fails miserably. So in that part, okay, it has to be completely data driven. And so you have to have, it takes care, the Geant4, okay, takes care of that, okay, I mean, I'll come to that thing, okay, later on. But the Geant4, okay, what it does, okay, that the user needs to use the Geant4 tools, and you have to tell the Geant4 kernel, okay, about the configuration. I mean, what is your detector? And then after doing that, okay, that is the initialization phase. So you have to tell, okay, I mean, what is the configuration of the detector, and what are the particles you try to simulate. Your particles. So is it a one particle you start to simulate? For example, you start with an electron beam, okay, I mean, of a fixed energy coming from a fixed point, or it could be an interaction itself, okay, I mean, which is described by an event generator. Okay, so that is free for you to free for the user to define, and all one has to tell the Geant4, okay, how you try to supply that information. So this is one thing which you have to do, and then when Geant4 takes care of that, okay, I mean you have to interact with the Geant4 kernel, okay, I mean as the simulation goes on. The simulation goes on in a way that you cannot just simulate just single particle or single interaction. You have to simulate, okay, a large number of particles, because it's a Monte Carlo method, and in Monte Carlo method, the more number of particles is you generate, okay, your convergence of your uncertainty of the what do you call, the integration is smaller and smaller. So that's why you come in, you have to generate a large number of particles.
You mean that suppose we are generating one particle at a time?
Yes.
Then we generate multiple simulation and call that large number of particles?
Yeah, that's right. Yeah.
One single simulation.
Yeah, I'm coming to that. Okay, I mean there is a concept of run an event. So you make one run. A run consists of n number of events, and in a single event, it may be you will have one particle of a given energy. Okay, so that's how that whole things are. Okay, and since the energies may be fixed, then you expect to see, okay, the same thing happening, okay, for every single event, but it is not. Okay, so because the whole thing is random, you see different things happening for all the events, but when you try to sum up everything, you'll get on average, okay, I mean a true picture of the interaction. Okay, now what the user must tell, okay, I mean during this, okay, the experimental scenario, that means, okay, I mean as I said, okay, this is geometry of the detector. The material, when I say geometry, it is essentially the sizes of the components of the detector, how you position the components inside the experiment. I'll give you examples, very specific examples later on. The materials in the detector, and then there is something, okay, I mean that not all parts of the detectors can get a signal out of it. Only certain parts of the detector can get a signal. So these are called sensitive part of the detector. Some parts of the detector only takes care of the interaction, but which degrades the passage of the particle, but it does not produce any extra signal. So these are called passive materials. So I think, but you have to provide both of them, both the active part as well as the passive part. Otherwise, you won't get a realistic picture of the things which is happening. So this is one set of information which you have to provide. The second set of information, okay, we have to provide is what are the particles which would be simulating, and also some sort of radiation environment. Okay, I think forget about the radiation environment for the time being, because most of the time we will not talk about radiation environment, but in a complex experiment, you have to provide also the radiation environment as well. Then the user really wants from Geant4 what's happening during the transportation of this particle. So it has to say which particles are to be tracked. So for example, whenever there is an interaction, there will be many types of particles which will be produced. Now, most of the particles would be like to track. But for example, if the neutrinos are produced, neutrinos, you know, I mean, that hardly interacts with the detector material. But if you want to track them, it's fine. But then you have to spend computing time. But most likely computing times are not very cheap. So you try not to track them. So that is your decision. No. It may be fast, but you have to when you track through any detector, okay, every time the detector is not okay. When I say okay, I mean how a particle is tracked, then you understand that tracking a particle, even if it doesn't interact, is not cheap. You have to really compute how that particle really travels to the detector. So that so I think okay, I mean tracking through the tracing the particles through the detector, you have to do. The only thing where you save the time, you don't have to have an interaction, so the cross section is high. There's been nothing which will come from the interaction, so that part is be different from neutrino. But otherwise, okay, to tracing through the entire volume of the detector is equally expensive for neutrino as well as the other particles. And which physics processes would be of interest? And I'll again okay show you okay those things and how precise the simulation is going to be. Obviously, when you have a more precise thing, you have to pay a price in the computing time. Now, once to go to the next page. Now, the thing is, when you try to design any, this is not a small software package. Okay, this is a fairly complicated software package, and this is not developed by one person. There was a group of people who tried to develop the things together. So obviously, the first thing they try to do is that they divide the tasks among the people. And when they're dividing the task, they're trying to say, okay, I mean, which task is to be given to which people. So obviously, when they try to develop independently, you try to group the course in a way they're fairly within a box. They're it only depends on code in that particular box. It does not depend on codes in some other box. And that's how we try to partition it. That's how the architecture of the Geant4 code is being done. Now you start at the lowest level, which is called global, which does not depend on anything. So everything, okay, like for example, look, I mean, you define a 3-vector or a 4-vector and things like that. Okay, so that I think is fairly straightforward. Okay, those things are required, and those things are in the global. Then you have materials. This again does not depend on anything. But when it comes to, for example, geometry depends on material, and it also has a dependency on the graphics and graphic representation. And that's how slowly the dependency grows. And you slowly grow up in the things. Okay, I mean, this is essentially the important thing. This is the physics processes, all the electromagnetic physics and the hadronic physics. Okay, that is where it goes. Then you have the tracking. This is a trace the particles through the detector. Then you have an event. Then you have a run, and then you read it out, and then finally, okay, the top level is the Geant4. That's how the dependency goes. So you have only one-sided dependency, and it is not a cyclic dependency. If it is a cyclic dependency, then it's always very difficult to develop the things in thing. And in addition to Geant4, okay, I mean you have to depend on something external dependencies as well. So whenever you try to install, okay, for example, Geant4 on your laptop, you'll find that okay, when you need other things okay to be installed as well, and some are you have to do, otherwise you cannot install Geant4. But the thing is, okay, I mean, this is some HEP utilities. Some at one point in time, okay, I mean, CLHEP is already a part of Geant4, so you don't have to worry about that. But there are something which is trying to make the libraries and things like that, which is called CMake. For CMake, you need the PTL. Then you have it depends on lots of things. Okay, for XML, XML is another language. Okay, for self-describing the data, and it is heavily you may or may not use it. Okay, I mean, but Geant4 okay, has always the facility of utilizing XML for transporting, for example, the geometry of one detector from one application to another application. So for that it uses XML, but since Geant4 uses XML, one has to really what do you call install. Okay, I mean these things. Okay, I mean when you try to do that. Okay. Okay. Now it comes to how Geant4 really starts. The first thing it has to anything. Okay, when you have to run a program, it has to have a main program. I'll at the very end of the thing, okay, I'll show you okay how the main program is written. But at the beginning of the main program, you have to initialize the program. So in the initialization phase, okay, they say initialize. You have to first of all construct detector. So you have to provide a class for detector construction. Okay. So in the initialize, the first you say you have the detector construction class. You have to essentially do some sort of a thing called construct the detector construction class. So within the detector construction class, the first thing it does is has to initialize the materials, because when it tries to define the geometry of the detector, you always need the materials, and the same material may be used in many different parts of the detector. For example, whenever you have any detector, you have got many parts are filled up with air. So the air could be used in many places. Whereas, okay, I mean, if you have a detector with silicon may be used only in one part of the detector. So I think the materials could be are defined always at the beginning, or at least okay, materials are not constructed. I mean, they are usually constructed when they are necessary. Okay, then I think okay, I mean, you construct the geometry, and finally, okay, when I come to that, okay, I mean the final thing is that okay, in the definition of the geometry, how you have to somewhere say the what you call the coordinate system. Without a coordinate system, you cannot really define the geometry. So the final at the end of the day, okay, we have to provide okay how the coordinate system is defined, and coordinate system is defined in a wall volume, and that is the top level volume. When I talk about the volume, okay, I'll tell you okay how exactly the volume is constructed. So that it gets the top level volume, and top level volume that is being returned to the main program. The second thing it does is has to say, okay, I mean, what are the physics processes you like to have? For example, what electromagnetic physics and what hadronic physics, okay, I mean, all these models to be initialized. So it has to again, okay, I mean, the physics process construction has to be done, and then it's activate all the physics process appropriate to experiment. The physics processes really need to know, okay, what are the materials which is used in the geometry, because according to the materials, all the constants for the for anything, so it depends on the radiation length, interaction length. From that, they try to formulate all the cross-section tables. So I think that this thing is needed before the physics processes are constructed. Okay, so that thing is then initialized and that is returned. So that is, once that is done, then you are ready, okay, to do this simulation.
Lots of code. What does this diagram and this arrow signify? How do you explain that?
This is one way of saying, okay, how exactly the flow of the code is.
Blocks of code in relation. Something like that.
Well, I think, okay, I mean, the blocks of code will come, okay, I mean, this is a, what do you call, normally you have to, when any program, what do you call, top high level program is constructed, you have to, it starts with some sort of a process. The first process is, okay, I mean, what you really want to get out of that particular program. Okay, so you have to give the input to say, okay, I mean, these are my requirement. These are the things I'd like to have. After that, the people try to do what they call analyze the whole process. This is called, so after you have the requirement, once the requirements are given, then you have the analysis, and then you design the code, and then you try to do that. So there is a language by which all these things are done. I'm not talking about that process. Okay, this is a object-oriented programming is a method, okay, by which is being done, and these are what they call instantiation diagram for that. But I'm showing you those things only to show, okay, how the code really runs it. You really do not have to go through the blocks through that. I'll show you when I try to show you how the geometry is constructed or how the materials are constructed, then you can see clearly, okay, how it is done. But this is in one shot to say, okay, I mean, how the whole program really wants to perform. Okay, this is a sketch of the program. Now, once you have finished your initialization, you are ready to do the event processing. The first thing you do, okay, you have a thing which is called beam-on. Beam-on is a command, okay, given to Geant4. And the first thing is, when you say beam-on, it just closes the geometry. That means up to that time, the geometry is open. That means you're free to, open means, okay, you're free to modify the geometry. But now you are no longer free to modify the geometry. Once it is closed, what Geant4 does, it tries to optimize within the geometry, okay, how it will be traced later on. So once it is there, obviously, once the geometry is closed, then the physics models are fixed, the geometry is fixed. So the rest of the time, with a fixed physics model, a fixed geometry, the events are generated. Okay, and then it really goes in a loop. You generate an event, and this is done by some sort of a thing which is called a primary particle generator. It generates the primary events. That means, okay, I mean, in most of the cases which I have given, it is a single particle, and the single particle has to be said, okay, where it starts, and then obviously that has to be done in an event generator, from event generator, and then it goes to event manager to process the event. And when this thing loops over, once that event is processed, it comes back and it comes back during the next event, and so on and so forth. And once this particular loop is over, that means you are asking, okay, you have to generate n number of events, then I think you can open the geometry, and you can then change the geometry and may go to a new geometry and so on and so forth. Now, event processing is done by having what they have a stack. You may have a single particle to start with, but even then a stack is necessary. Why? Because this particular particle, when it is traced, it will interact and it will be producing other particles. Okay, so those particles has to be tracked again. So when it happens, obviously a new particles are produced. This particle is put into the stack. Okay, but Geant4 does the process one track at a time. It does not process all the tracks at the same time. So it processes only one track, and it asks the tracking manager to track it. You can see there are always lots of managers, okay, in the whole thing. When it's track, tracks are done in steps. I'll come to the steps later on, okay, but it's done in steps, and that is done by a stepping manager. And when the track finds itself, okay, that is nothing else to be done, okay, I mean it returns again back to here, and then tries to pop another next thing from the stack. And this thing goes on till the stack becomes empty. That means, okay, I mean, all the particles are tracked, and then you say, okay, I mean, this event is finished. Okay. Now we come to all the jargons, okay, one at a time. Okay, I have already talked about run and event. Okay, I mean, event is a run is a collection of events which essentially share the same detector setup and physics conditions. As soon as I said, okay, I mean, your geometry is closed, that means, okay, your physics conditions are kept the same. So I think, okay, I mean, then I think, okay, I mean, you have essentially start with a run, and you may have multiple runs with the same conditions. Okay, there's no harm in doing that, and the reason for that is that, okay, I mean, you do not want to have your computer busy for years together. You want to run for a number of hours, okay, and then you stop, and then you may start again, okay, for another number of hours. So a run consists of one loop over events, and within a run, the user cannot change the detector setup or setting of the physics process. So that thing is fixed, okay, during a run. And the thing is, okay, all the terminology, the beam on, is a terminology is normally happen in any nuclear physics or energy physics experiments. You have when beams comes, I mean, what normally happens is that the beams are accelerated in an accelerator, and when they come to the experimental area, obviously, okay, I mean, you have radiation, okay, they usually say beam is on or beam is off. When beam is on, obviously nobody can really approach that area. So beam on means, okay, I mean, the thing is active, and so Geant4 also utilizes the same terminology as beam on. Now, at the beginning of a run, I said it closes the geometry, but what it means when it closes the geometry is really optimized for navigation. And the cross-section tables are calculated as at the same time. I'll tell you how when I talk about geometry, I'll say what I mean by the optimization. Now, normally when you define a detector, you can put within this detector, you have a big volume. Within this volume, you can place many other things, so on and so forth. Okay, so that is one way of defining a geometry. Or you may be also can do one thing that this particular box may have five equal divisions along this. Is it 1, 2, 3, 4, 5, 8? Now, when it tries to trace a particle in this particular big volume, the way it has to say you are here and you try to trace it, and you know this particle is in this direction here. How you try to compute how far you have to go? It has to say, okay, along this thing, it tries to see, okay, what is the distance to reach this particular volume. It also has to see how far it has to go to this volume, or this volume, or this volume, or even this end of this particular mother volume. So it has to really compute this. Now, so it has to compute these things. But if you are in here, for example, here all it has to do, how far it has to reach, in this case here, or in this mother. Okay, so it is only 2 computations it has to do. Now, the other thing is, okay, if you have it is in 5 identical things, sometimes it is very, very easy, okay, to compute this distance rather and this distance. I think in many cases when you are dividing the whole thing in equal parts, the computations are easy. But here, okay, you do not know first of all these shapes, so the computations are difficult. Okay, not difficult. Okay, you have to do all these computations. But one easy thing which geometry tries to do is tries to have a, for example, it tries to have artificial partitions. Okay, now if it is in here, all it has to do is it has to say the mother and it has to say in this particular partition. If it already finds in this particular partition that it has got a length, it doesn't have to go to this partition at all. So you are saving some time, okay, of computing the thing. So this way of dividing the whole thing into various blocks. Okay, this is an optimization for the thing, and this particular optimization is done. Okay, when the geometry is closed. Now, as I said, okay, for everything, okay, there is a manager. For a run, there is a manager which is called a run manager, and yeah. But if you find a hit in the first partition, then you don't have to go to the second one. Huh? It is a large factor because the geometry is really complex. I'll show you how this is called voxelization, and that really saves the CPU time, okay, by at least by factor of 4 and 5. And you can do this voxelization not in one dimension. You can do the voxelization in 3 dimensions.
Narrow down the search.
Yes, essentially narrow down the searches. I think, okay, in a detector today, okay, I mean, you usually have millions of components. So it's not just 5 or 10, okay, it's millions of components. So you don't have to really compute, okay, through all these millions of components. That is one way. And the other thing is that for every given component, okay, there is an user action class. You may have a user action class, okay, for runs as well. But I think, okay, we hardly use, okay, the user action class in anything. Then we go to the event. That is the, as I said, okay, this is the basic unit of simulation in Geant4. Okay, so this event is essentially your process. You start with one particle, or you start with one interaction, which could be PP collision event, and then you process that. So at the beginning of the processing, the primary tracks are generated. Okay, so this could be one single particle or several particles, and they are pushed into, as I said, okay, into a stack, and you start with a you pop up one of them, and that is traced to the detector, which could result secondary particles. And if there is any secondary particles are produced, they are pushed into the stack. But it's just pushed into the stack, and if the track is not, for example, is killed, it will keep on continue with the same track. For example, when you have an electromagnetic shower, an electron Bremsstrahlungs, a photon is produced, the photon is kept into the stack, the electron continues, it produces another photon, that photon is again put into the stack and continues and continues. So till the electron loses all its energy, then I think the electron is finished, then it comes back and start with the last photon in the stack and start processing that. And the same thing continues, and as I said, okay, I mean, it comes with a push and pop, and till the stack becomes empty. That means the processing of the event is over. And when you have the end of the processing of the event, you have a list of vertices and the particles as inputs, and you may store, okay, some information in the form of the energy deposit in the sensitive part of the detectors, which is called hits, or is the path of the trajectories of some particles. So this could be the output of the processing, and you keep this information in something which is called in the event, and this is managed by the event manager. And you can have a user, as I said, user action class. Okay, but for that, for everything there's a user action class. No, last in, first out. Yeah. Yes. Yes. You keep. Yes. Next event, okay, and then it is still inside the same event. when that particle is finished, it takes out the last particle which is produced, which is put in the stack. So as I said, it's last in, first out. It's a LIFO mode. Okay. Now, a track is essentially a snapshot of a particle. That means, okay, it only says, okay, at the currently what is the property of that particle is, where it is, what's its momentum and all that stuff. Okay, I mean all the attributes of that particle is. It is only a snapshot. So as the particle is traced, obviously that snapshot keeps on changing. That means the track really changes its attributes all the way through. So this is something to be remembered, that it is not something which is really kept in memory. So it keeps on changing its content, okay, as the time goes on, as it's the thing. So, and at the end of the thing, okay, the track object is deleted when it really goes out of the world volume. That means, okay, it really escaped the detector, and you don't have to worry about where it has gone, or it disappears either through decays, or it has done an inelastic scattering. So obviously, okay, you produce other set of particles. For example, you have a photon has a pair production, then obviously the photon will disappear. You have only a pair of electrons and positrons. Okay. That is in inelastic scattering. Or it goes down to zero kinetic energy, and there is no at-rest additional process is required for the particle. You have at-rest processes like when a muon stops, it can be captured or it can decay. Okay, so I think that there is at-rest process for muons exist, but for many of them, okay, there's for electrons, for example, there's no at-rest process, or the user decides to kill it. Just I don't care. Okay, I mean I don't want to see it further. Okay, so I just kill it. So no track object persists at the end of an event. So I think when the event is complete, obviously there is no tracks whatsoever. So if you want to keep information about the tracks, they provide what you call a trajectory class. In a trajectory class, okay, you can keep the history of the track if you want. And again, okay, I mean there is a tracking manager which manages the processing of a track, and this is what is called a G4 track, and then there is a user tracking action like anything else. Now, the track is, as I said, okay, it is traced through the detector in steps. Here you have, for example, one volume, and this is a separate volume, and maybe, okay, there is nothing else happens except that, okay, I mean it starts from here and it reaches the boundary. So you have a step within the same volume. You have a start point and an end point. This is a pre-step point and this is the post-step point. Now, it may happen, okay, the post-step point could be here also. That means at this particular point, there may be interaction. It could be at the boundary crossing. It could be anywhere within the same volume itself. But it has always a step has got a pre-step point and a post-step point. Okay. Now, yeah, or if it is a boundary crossing.
So a step is only defined between interactions. So it can't be like for an interaction there are 3 steps, 4 steps.
The thing is, okay, in principle, sometimes, okay, I mean you may have multiple steps if it depends on the precision of the thing, of the tracking. There's an important thing which happens is that multiple scattering. If there is a multiple scattering, what happens is that, okay, it's not an interaction which takes place, but you're essentially continually changing the direction of the particle in a multiple scattering. So if your multiple scattering alters the direction of the particle by a large amount, then maybe, okay, I mean, you have a step without interaction, but is limited by multiple scattering. It is very similar to limitation of the boundary crossing. Here there is no interaction has taken place, but you have got another point. So you have always in a step, you have a pre-step point and a post-step point. Whatever the cause of this particular step could be interaction, or could be boundary crossing, or could be something which really limits that particular step, which may be decided by your the thing. Now the thing, okay, I mean, the boundary crossing is a very special thing, because the pre-step point is in this particular volume, whereas the post-step point, though it is in the boundary, it really refers to this volume. It's not refers to this volume. Now, since it is really at the boundary, all the things which can happen at a boundary can be simulated. There is one thing which happens at the boundary normally is something is called transition radiation. That really, or a reflection, or a refraction. These are the things which can happen at the boundary. So these things can be simulated in Geant4 by defining the post-step point at the boundary. And as I said, okay, I mean, there is a manager class and a user action class everywhere. As I said, okay, I mean, a track cannot be there, okay, at the end of an event. So they have provided something that's called a trajectory, and to keep the history of a track, okay, during this passage of the particle. Now, you may worry about the trajectory, you may not worry about the trajectory. So it is up to the user to use a trajectory or not. Not necessarily, okay, unless you want to visualize the whole thing. Obviously, you do not. I think, for example, when you have a large-scale simulation, we really do not worry about the trajectory. But if you want to see the picture, okay, how that interaction has taken place within the detector, a trajectory class is sometimes, okay, I mean, illustrates, okay, I mean, how the particle has gone through the detector, okay, I mean, and where the interactions have taken place, how the showers are generated. All these things, okay, can be utilized, okay, for having a trajectory. So, so I think, okay, I mean, trajectory is a collection of something which is called a trajectory point, which essentially trajectory point is a class which gives some of the information of a step object. Okay, so I think, okay, I mean, as I said, okay, I mean, track is not a trajectory, or trajectory is not a track. Track keeps on changing its properties as the tracking goes on, whereas trajectory is to some extent, okay, I mean, it keeps the history of the track. And similarly, okay, I mean, a step is there present only during one particular step, whereas a trajectory point keeps information of the step if you want to keep it. Now, obviously, okay, I mean, the trajectory or the trajectory point does not keep all the information of a track or the information of the step. Otherwise, okay, I mean, you can keep all of them. Okay, I mean, the whole purpose of saving the information is gone. Okay, so you keep a minimal information which can help you, okay, for the visualization, for example. And I think it's apart from visualization, I do not see, okay, I mean, where trajectory or trajectory point has an important role to play. But they have to be there, okay, I mean, because one of the most important thing when you try to simulate is to validate the whole process. For the validation, you need the visualization. Now comes a particle. Now particle is present inside Geant4 in many forms. You start with a what you call a particle definition. That means, okay, this contains the static properties of the particle, like the charge, mass, lifetime, decay channels, branching ratios, and all that stuff, okay, which you know, okay, for that particle. So if you have a pion, for example, it could be have a charge of +1, mass of 139 point something in MeV. It has got a lifetime of something of the order of 10 to the minus 8 seconds, and it decays, okay, I mean, dominantly to mu plus and neutrinos. Okay, so I think those properties, okay, I mean, are the static properties of the particle. And you have to have the process manager which describes the process involving the particles. Okay, so obviously there is for every single particle there will be a process manager for a pion. Okay, I mean, obviously, okay, how a pion can be processed, okay, I mean, in what type of processes it can happen. So that is says, okay, I mean, and up to that, okay, is there. Then you go to the dynamic particle. I mean, that is the thing, okay, where you have a particle definition, but you add to that things like which is the dynamic properties of that particle, like a momentum, energy, spin. These are the things are attributes of the dynamic particle. It's not in the static particle definition. And when you have a G4 track, it has its own unique G4 dynamic particle object. So, and then you have a G4 track. In G4 track, in addition to this thing, you add the position and the geometrical information. Like this particular particle is in this particular volume. Okay, it has this. You can, but everything. Secondary particle starts with a particle definition. Secondary particle, obviously, it can be the same. Yeah, there will be class, okay, but the objects coming from the class will be different. Class essentially defines, okay, the properties of the thing, but when you goes to a simulation, okay, I mean, you can have multiple objects belonging to the same class. Okay, so that's the main thing is that, I mean, you have for example, you have electrons, and you have got not just one electron, you have got millions of electrons, okay, which is produced in the shower. But all these electrons are electrons. So they have, the particle definition is the same. That's also, if it is electron, it is electron. The property of the electron is the same. It doesn't change. Oh, sure. This is a different particle. It could be a muon, for example. It could be a pion, for example. It could be a neutrino, for example. Everything which you have could be, okay, I mean, it could be stable particle, it could be unstable particle. Yeah. For every particle definition, okay, these are essentially can be defined by a static class. Okay. But once you add momentum and energy, okay, this is no longer a static class. And when you add position, okay, obviously, okay, I mean, it's much more dynamic. Now, comes to the really tracking, okay. The thing is, okay, I mean, it's important to know tracking in Geant4 is universal. It is independent of the particle type. So if it is a electron or a pion or photon, whatever it is, okay, I mean, it does not really matter to Geant4. It is, the procedure is always the same. Also, it is independent of the physics processes involving the particle. That means, okay, I mean, if it's an electron, obviously you have got only electromagnetic interaction. If it is a neutrino, it is only the weak interaction and the particle propagation. And obviously, okay, I mean, particle propagation is common to every single particle, but other processes can differ, okay, from them. So what it does, okay, I mean, the way it is done is that it gives the chance to all the processes. Okay, so when you have a particle, it can have n number of processes. One is the transportation, one is the interaction, and maybe, okay, I mean, decay is also one type of interaction. So it gives all the processes, okay, I mean, which you have, okay, I mean, maybe have several types of interactions which it can take place. For example, a photon can have pair production, Compton scattering, photoelectric effect, Rayleigh scattering, reflection. All these processes are there. So I think, okay, I mean, all this you ask Geant4 ask all these processes to essentially contribute to determine which limits the step length and which can contribute to any possible changes in the physical quantities of the track and which can generate the secondary particles. For example, when you have a reflection, that does not generate a secondary particle, but when you have a pair production, it will generate electrons and positrons. Okay, so I think, okay, so, and it will suggest, okay, I mean, all the processes changes in the state of the track. That means, okay, I mean, you want to change, if you want to keep the particle, you postpone further processing or to suspend it, okay, for the time being. And these are things, okay, we don't have to worry too much about it right now. Now comes the process. I think process, as I said, okay, these are essentially the normally, okay, I mean, any interaction, okay, is a process. Any types of interaction is a process. But in Geant4, transportation is also considered as a process. So that means, okay, by which a particle really interacts with a geometrical volume, boundaries and fields of any kind. If it's an electric field or if it's a magnetic field, okay, that is also a process. So I think, okay, and since in Geant4, okay, I mean, this transportation is also a process. The shower parameterization process, if you want to parameterize the shower, it can really take over the ordinary transportation without really modifying the transportation process itself. That means, okay, I mean, it is really, I mean, transportation process is defined and shower parameterization process is defined independently. So you don't have to worry about each other. Okay. Now, what happens what the process does? The process has to provide what should be the length that particular process will give rise to the distance at the end of which, okay, there should be an interaction or something will take place. So if you have n different processes, it will try to inquire all these processes, what should be the interaction length for that particular process, both in space and time. And the shortest the distance which it provides, that is the thing which will say decides this particular process is going to limit that particular step. Now, you have several things which can happen. Okay, I mean, you can have a process which is at rest along a step or a post step. Now, at rest means, okay, I mean, the particle has really come with at zero kinetic energy. Now, at rest, okay, I mean, you may have a process like it can decay. I have talked about it in the past. Okay, it can happen, or it can. There is no process. It can have no process whatsoever. If there is no process at rest, okay, obviously the track can be killed. Along a step, okay, that means it's a continuous process. Like there is something is called Cherenkov radiation. Again, I have not talked about it. Okay, that's a continuous process, or even continuous energy loss. That is a continuous process. Okay, and obviously, okay, I mean, there's a post-step process, which are all discrete processes. That means, okay, at the end of the step, if you have, for example, if you have a we call it pair production at the post step, okay, that particle has to disappear, and you have a pair of electrons and positrons produced, or you have a decay in flight, for example. So all these things, okay, I have, and obviously, okay, I mean, you have to provide the track status, and the status could be alive. The track is alive. It is stop but alive. It is stop and kill. This is stop and kill. This is kill and secondaries. Suspend the particle. Postpone to next event. So this status is internally used in Geant4. Okay, I mean, you don't have to worry about it. Depending on the status of the thing, okay, when Geant4 takes an action on that particular track. Some cases, okay, you can provide these things. For example, okay, I mean, when you are doing some sort of parameterization, okay, I mean, you can that particular parameterization takes over, and then you kill the track. So you have to say stop and kill. But apart from that, okay, you don't have to provide any track status, okay, to the particles. I mean, these things are useful, okay, to know, but it is useful only when you are doing, okay, I mean, a much more complex simulation. Okay. Similarly, okay, when you have a step, okay, I mean, step also has a status. Now, you have the pre-step and a post-step. So the post-step point really gives the status of this particular step, and pre-step point provides the status of the previous step. Okay, so you have reached this particular step here, and then you are considering the step. So there is a previous step to that, and pre-step point, okay, I mean, provides whatever the particular step point status is the status of the previous step. So the things is that are you in the boundary of the with the world? That is sometimes very important, or is it in the geometry boundary? And if you are at rest, or if you are some user defined limit, these are the things that come in is provided by the Geant4, and according to you can take actions. For example, when this is the thing, you can always utilize the geom boundary and the world boundary, to take some very specific things which you want to do. And many time, for example, when you are doing a Cherenkov radiation, usually in a transition radiation, obviously transition radiation takes place at the geom boundary. So obviously, when you are at a geom boundary, then you say, depending on that particular type of boundary, you can emit the what you call a photon for the transition radiation. The how long we are gone? Huh? Across 1 hour? They will take more? See, okay. This is a place where the stacks is just coming in, okay, so maybe a good place to stop also, okay, but this is a good place to stop, but I don't know, that will take quite some time. No, I think I better stop here, okay, because in the next class, okay, I'll try to talk about the geometry. Then I think, okay, I can come to the stack and then come to the geometry. No, I think it's better stop here. The problem is always, okay, why it is complex is because it's a somewhat general thing. Okay? Whenever it is something general, we try to see all particular possibilities, and that's why, okay, the heart of Geant4 is the tracking. Because that is a place, okay, where really Geant4 is, because without the tracking, okay, you really can't do that, and that is really the complex part of Geant4. I think it is not a user interface, okay. The user interface is essentially the geometry definition and recording of heat definitions and recording of heats. But that is much simpler. I'll send you, okay, up to this spot. Where I stop, okay, this afternoon. Once I go back home, I'll send you this. Yeah.
So there is the data set. What is this? This is the physics of it.
The data sets are essentially, I said, okay, the part of the simulation is data driven. So those are the things which is required, okay, I mean, to do that thing, okay. Some of this, particularly if one looks at the low energy hadronic interaction, it's entirely data driven. So you look at the cross section tables and things like that, okay, from the thing, and that is used. For some of the other things, okay, they are parameters used in the thing, okay, in some cross section calculations and all that. But that is also a large amount of data which is there. So all these data are required, okay, I mean, in running the Geant4. So the thing is, okay, I mean, for installing, okay, I mean, you, at the time of the installation, the only thing, okay, one has to define where the path of the data are. But the data has to be downloaded as well.
What does this CMake does? You down.
Yeah, the thing is, whenever you tries to make the libraries, previously, okay, there used to be some mechanism called gmake. It is a GNU command, okay, for essentially trying to run that. But later on, okay, I mean, they came up with this this CMake thing, okay, which is coupled to this PTL thing, and that is required, okay, to really make the libraries. Once you run get the code and want to make the libraries, they ask you to do a CMake command, okay, for doing that. And I'm very poor in that thing myself, okay, so I do not want to install any Geant4 library anywhere. But the person who is in charge of doing that, okay, I mean, he's a sound guy. There's two persons who are doing that. One is a Britisher, Ben Morgan, and Gabriele Cosmo. So they have set this thing up, and one just blindly use those commands, okay, to get them installed. Well, sometimes, okay, I mean, you can have already a pre-installed library. Then I think, okay, I mean, for making the library is not required. But you have to eventually make your own executable for Geant4. Then you have to essentially use the CMake commands for doing that. And usually when I have issues with this, okay, I have one person at Shah Institute, okay, who happened to did his PhD with me, and I go to him, okay, and ask his help. His name is Shubir, okay, what is his surname? Sarkar, Shubir Sarkar. And I think if you really, I can provide you, okay, his email address, and I can ask him, okay, I mean, if you run into any issue, okay, can send it to him. Yeah, at some point in time, when Shubir asked me to give the same thing, okay, to people in Shah Institute, okay, so. But I don't know when it will happen, okay, so. You see, what happens is that, okay, I mean, in the course of your career, okay, I mean, you come across with people who happen to be a student, and sometimes your student do much better than you in some areas, okay, but obviously, okay, I mean, we have not all the things, okay, I mean, and one has to go back to the student, okay, to learn from the student, okay. Yeah, I think, okay, I mean, yeah, but to understand the software better, that's why I'm trying to tell you about this thing. Rather than to be blind to the software, okay, I mean, it's essentially trying to illustrate what the software does. And when it comes to a given application, one really has to define only a limited number of classes. I'll come to that at the very end. You can say okay, what are the classes you have to define. Obviously, you have to define the main program and a few classes, so 5 classes, I think, altogether. Then I think we'll come in anything is complete. At least a basic program in Geant4 can be completed with the definition of 5 classes. And beyond, I mean, it can, but when it comes to a complex application, okay, when you runs into hundreds of thousands of classes at the time. Yeah. Okay. I don't know how to switch it off. Yeah, one of the good things is that okay, I mean, did anybody connect from outside? Oh, he connected. No, no, we have given the address, but I'm not sure he's connected. Right. Very good. That feature should be